Welcome to Lesson 4 in Multiple Regression. As always, let's start by going over today's goals. We'll learn about multiple regression, make a figure for data for a multiple regression, do a multiple regression in R, and summarize the results in our Markdown document. Now you may remember that a couple lessons ago, we ended with this figure. This was the data for my name Page from Lesson 2. We found that there was no effective year on the popularity of the name Page. When we colored our data points by sex, and then built separate regressions for each sex, we found that there does appear to be a strong effective year. It's just different for females and males. This is known as an interaction, and today we'll learn how to build a model that accounts for potential interactions in our data. Let's start with the math. Here is our equation for a linear regression with a single variable that we've seen many times at this point. But what if you have not one, but two variables, as we did in the name example? Well, then we get an equation like this. The equation is largely the same as our equation with one variable, except we add this b2x2 part of the equation to represent our new variable and its slope. We also have to rename our original b and x to b1 and x1. Okay, let's break down this equation a little more. Our yi is a specific y value. Our a is still the intercept. Our b1 is the slope of our first variable. Our x1i is the specific x value for our first variable. Our b2 is the slope of our second variable. Our x2i is the specific value x value for our second variable. And as before, our ei is the random variance or the residual. Okay, this should be for the most part pretty similar to our linear regression equation with only one variable. But to be sure it's all clear, let's use a real-world example. I'm still using the baby name data, but instead of looking at the name Page, I compiled the 20 most common names in 1901 for both females and males, and looked at their average popularity in the first half of the century, 1901 to 1950, and the second half of the century, 1951 to 2000. So on the x-axis, we have each half of the century, first and second, and within half century, we have sex, female and male. So we can probably expect that names that were popular in 1901 will be less popular in the second half of the century than the first. But we don't know what the role of sex will be. Okay, here's our figure. Indeed, we seem to have an effective half century, where these specific names are in general less popular in the second half of the century, but the magnitude of the effect doesn't seem to be the same for each sex, suggesting we could have an interaction. Actually though, what we're doing with this equation above isn't looking at the data like this. Instead, we're looking at the effective half century collapsed across sex, and the effective sex collapsed across half century. Just as in our previous lessons, we can build separate linear regressions for each variable. Let's also pull away the boxes so we see our individual data points. Now we can go through the equation the same way we did in the previous lessons. I'm going to skip some variables that should be familiar to you and only focus on specific parts of the equation. Starting with the half century analysis, first we can draw a regression line connecting our two levels. Our a, or intercept value, is the mean of the default category, here first half a century, since it is 0 in our equation, and our b, or slope, is the difference between our two levels. We can do the same thing for the regression with sex as a variable. We draw a regression line, and we see that a is the mean for females, and b is the difference between females and males. This is great. What we really want to know is how this connects to our equation with both variables together. Okay, let's pull away these simple equations and focus on our multiple regression. The transition to our multiple regression is actually very simple. b1 is simply the slope of our first variable, and b2 is the slope of our second variable. Same as in our simple linear regressions. But you may be wondering, what is a? Well, a is complicated. There's no straightforward way to talk about what a is in the way it has been for our simple regressions. The problem is that the model is trying to find an a that is good for both of our variables at the same time. This discussion on stack exchange is the best explanation I've found. Basically, just be aware that the intercept in a model like this is less informative than in other models where you can say it's the mean of a certain level of a variable or the value of y when x of a certain variable is 0. Let's move on to the actual R code now. At the top of our mathematical equation, and here is our R code. As you can see, we still use the LM call we used before. Also, as before, the first part of our equation is our y value. Then after the tilde, we have our first variable, a plus sign, and then our second variable. That's it. All you have to do to run a multiple regression in R is your same LM call, but add together your two variables. As before, we can also call a summary on our model. The estimate of the intercept refers to A in our model, but as discussed, it's not very informative. We can also get the slope for B1, the slope for B2, as the estimates of our two variables. Finally, we can use the resid call and get the residuals of our data points. Great, we've now successfully run a multiple regression in R. I want to take a moment now to see how our multiple regression compares to both of our simple regressions with only one variable. Here's the model with just century half as a variable. Here's the model with just sex as a variable. And here's the model with both variables. What I want to draw your attention to is the estimates across the single variable models and the multiple regression. Looking first at the estimate in the model with just half century, we see that it is exactly the same as in the multiple regression. Likewise, the estimate in the model with just sex is the same as in the multiple regression. You should be aware, though, that this is only because the data set is fully balanced. I made a point to have exactly the same number of data points in the 2x2 matrix of century, half, and sex. If you have unbalanced data, the multiple regression will take that into account when computing the estimates, so they will be a little different from your single variable models. Okay, we now can make a model with two variables, but you may be thinking, I thought the whole point of this was there was an interaction. This model doesn't account for that. Well, now that we understand an additive multiple regression, let's run a multiple regression with an interaction. This takes us to part 2 of our math lesson for today. Here's our new equation for a linear model with two variables. Right now, the model is just additive, but we want to include an interaction. All we have to do is change our plus sign to a multiplication sign. This equation actually expands out to something like this. Now the top part of the equation looks just like our original multiple regression. What's new is this B3 coefficient. Typically, we've talked about coefficients as being slopes of a variable, but here B3 is multiplied by both B1 and B2, so it can be thought of as the slope of our interaction. Okay, let's break down each part of our equation. yi is our specific y value, a is our intercept, b1 is the slope of our first variable, x12 is the specific x value of our first variable, b2 is the slope of our second variable, x2i is the specific x value of our second variable, b3 is the slope of our third variable, but instead of variable, we really mean the slope of our interaction, and finally, ei is our random variance. Now let's take all of this and go back to our real-world example. Now that our model includes interaction, it makes sense to look at this figure with all the data separated by both variables. To understand what each part of the equation means is a little complicated, so I'm going to change our variable levels to zeros and ones like we did in the past. So now we change the levels of half century so that first half is set to 0 and second half to 1. I've noted that this is for x1 on the axis label to keep our two x variables separate. Similarly, we can change the levels of sex so that female is set to 0 and male to 1. Now we can refer to each of the boxes in our box plot as a combination of zeros and ones for x1 and x2. For example, our first box is the data when both x1 and x2 are set to 0, or when half of century is first and sex is female. Our second box is when x1 is still set to 0, first half of century, but now x2 is set to 1, male. Our third box sets x1 to 1, second half of century, but x2 to 0, female. Finally, in our last box, both x1 and x2 are set to 1. So this is all the data for the second half of the century for males. If this is unclear, feel free to take a moment to pause the video and make sure you understand the labels in each of our boxes and how it relates to the labels of our two variables. Okay, Now, connecting the pieces of our equation to the figure is actually in some ways easier than our model without the interaction. Our interceptor, A, is equal to the value of y when both x variables are set to 0. So, it is the mean of our first box. See how both x1 and x2 are set to 0 here. Now, let's look at our betas, or the slopes of our variables. The way a multiple regression with an interaction works is instead of looking at a given variable collapsing across the other variable, we actually only look at a subset of the data given the baseline of the other variable. Starting with x1, or century half, we're only going to look at the data where x2 is set to 0, female, giving us a picture like this. See how I've pulled away the two boxes where x2 is set to 1. So when interpreting the effect of x1, century half, we only compare data where x2 is 0, the baseline, in this case female. Then we draw a regression line, just as we have before, and our b1 is the difference between these two boxes. To get the value of b2, we do the same thing. We compare the difference between when x2 is 0 to when x2 is 1, but only for when x1 is set to 0. That would give us a figure like this. Once again, I've pulled away the boxes where x1 is set to 1, our non-default level. We draw a regression line, and then b2 is the difference between these two boxes. Okay, the last part is probably the trickiest. To get our value for b3, we need to take into account all of our values thus far, a, b1, and b2, to get b3. To calculate b3, we take the mean of our fourth box, when both x1 and x2 are set to 1, and subtract a, b1, and b2. If this is confusing, don't worry. This can be really complicated the first time you're trying to interpret models like this, but with more practice it becomes second nature. To try and make things a little clearer, I've made a table to give you equations to get the means of each of our boxes. Our first box, where both variables are set to 0, is equal to a, or our intercept in the model. Our third box, where x1 is set to 1, but x2 is still set to 0, is equal to a plus b1, where the first box plus the slope of our first variable. Our second box, where x1 is still equal to 0, but now x2 is equal to 1, is equal to a plus b2, where the first box plus the slope of our second variable. Finally, for our fourth box, where both x1 and x2 are set to 1, is equal to a plus b1 plus b2 plus b3, where b3 can be thought of as the slope of our interaction. Feel free to pause the video now to look over this table for clarification. The important thing to take away from this is that at no point are we looking at the grand mean of the data or the mean of a variable collapsing across another variable. To give you a better idea of what I mean by this, let's look at just the b1 x1 part of our equation for both the model with the interaction and the model without the interaction. In the model without the interaction, to test the effect of x1, or the effect of half century, we look at the data points in each half century collapsing across x2, sex, and get the difference between these boxes to get our b1. Conversely, in a model with the interaction, to get b1, we only look at the difference for half century given that sex is set to the baseline value. And that difference is our b1. Okay, let's now get to our R code for our new model with the interaction. Here's our updated equation including our interaction term, and here is our linear model call. The only difference from our previous call is we're replacing the plus sign with a multiplication sign. The rest is the same. Our y values still come before the tilde, both x1 and x2 after the tilde. We can also call summary in the model to get our coefficients. Remember though, now our intercept is actually informative. So here, the estimate of the intercept is the mean of the data when both x1 and x2 are set to 0. So the first half of the century female names. Our b1 is the estimate for half century half, given again the baseline of females for x2, and our b2 is the estimate for sex, given the baseline of first half of century for x1. Finally, our b3 is less transparent, but tells us the slope of the interaction. The larger the estimate, either negative or positive, the more likely an interaction is present in the data. As always, we can also use resid to find out the residuals for the data points in our model. Looking at the results of the model, we find that in this data, we do indeed have a significant interaction of century, half, and sex. But as it stands, we don't know what that means. We know that for females, there is a significant effect of century half, such that popular names from 1901 were less popular, as shown by a negative estimate, in the second half of the century compared to the first half. And we also know that in the first half of the century, there was a significant effect of sex, such that popular male names were more popular, as shown by a positive estimate, than popular female names. But we don't know, for example, if the effect of century half is also present for males, or if the sex effect is present in the second half of the century. So to do this, we're going to slightly change our LM call so it looks like this. The important change to note is this re-level call here, where first we write our variable, and then the level that we want to be our default. So before, our default for century half was first, but with this call, we change it to second. As before, we can run our summary call and get our A, B1, B2, and B3. And of course, we can call resid and get our residuals. Now the main reason we did this was to see if the effect of sex would still be present, even if the baseline for century half was changed to second. And we see that it is still significant. To really understand what's going on though, let's compare all of our multiple regressions. First, we have our multiple regression with no interaction, and our multiple regression with the interaction. Comparing the estimate for the effect of century half in our first model to our second model, we see that the effect is larger, a larger estimate in our second model. This means the effect is larger specifically for when only looking at data from female names compared to looking at data pooled across sex. We can do the same thing for our effect of sex, comparing the first model to the second model. Now here we see the effect is larger for the model without the interaction. So the effect of sex is larger when the data is pooled across century half than when specifically looking at the first half of the century. Okay, now let's bring on our model where we change the baseline for century half. Now we can see how our estimates change when we re-level century half to second, starting with the intercepts. Recall that the intercept is the mean of when all variables are set to the baseline, or 0. In the first model, the intercept is the mean of the data in the first half of the century for females. In the second model, the intercept is the mean of the data in the second half of the century, since we changed the baseline for century half, but still for females, since we didn't change the baseline for sex. We can see that the estimate is a larger negative number in the second model, suggesting that popular female names from 1901 were less popular in the second half of the century than the first. Turning to our effects, for the effect of century half, we see that the estimates are the same, just with opposite signs. That's because in the first model, the baseline is first, and our estimate tells us how second, the non-baseline level, compares to first, the baseline level. And we see that the estimate is negative, showing that popularity goes down. By switching the baseline to second in the other model, we also flip the sign of the estimate, because now our estimate tells us how first, the new non-baseline level, compares to second, the baseline level. And we see that the estimate is now positive, showing that popularity is larger in the first half of the century. However, moving to our estimates for the effect of sex, this is where things start to change more. In the first model, the effect of sex is given the baseline of first century, but in the second, the effect of sex is given the baseline of second century. The effect is significant in both models, but larger numerically in the second half of the century. So one way to interpret our interaction is to say that there is a difference of sex in popularity of names in both century halves, but the magnitude of that difference is larger in the second half of the century. If you take a moment to go back and look at the figure, you'll see that this interpretation matches what the figure showed us. Finally, the estimates for the interaction are also the same, just with flipped signs, for the same reason as why the effect of century half had the same estimates, both flipped signs. If you're still not totally clear on all this, pause the video and take a look at all of these summaries, and see if you can understand where and why estimates are the same or different across the different models. We'll now turn to the lab, where you get the chance to build your own multiple regression. Today, we'll be looking at data from Star Trek. More specifically, we'll be using data from the various alien species encountered on Star Trek and whether they are expected to become extinct or not. This data comes from the Star Trek project, which provides lots of interesting visualizations of data from the Star Trek universe. To test our questions, we'll be using logistic regression, and we'll ask 3 specific questions. 1. Is a given species more or less likely to become extinct in one series of Star Trek or another? Today we'll be focusing on just 2 series, Star Trek the Original Series and Star Trek the Next Generation. 2. Is a given species more or less likely to become extinct if it is a friend or foe of the Enterprise? For anyone who doesn't know, the Enterprise is the main starship on Star Trek across these 2 series. And finally, is there an interaction between these 2 variables? We'll start by listing our model variables. Our yi here is likely to become extinct or not, expressed as 0s, not likely, and 1s, likely. Our a, we don't know, we'll get from the model. Our b1, we don't know, we'll get from the model. Our x1 is series, the original series or the next generation. Our b2, we don't know, we'll get from the model. And lastly, our x2 is alignment, friend or foe. Remember, because this is a logistic regression, we don't have an error term. Pause the video now to do the lab. Come back to the video when instructed to learn more about some of the code we'll be using today. You were just introduced to the package per, and we used it to read in several files of the same structure at once. Let's go through each line of new code. First, we have our list.files call. This simply tells R we're going to be getting a list of the names of all the files in a certain location. This path call tells R where to look for the file that's going to list. In this case, the path is just data, since our files are in the data folder. Next, we say we want R to remember the names of the files, including the path where they're located. That's what's going on with this full.names equals true. We're saying we want R to save the file name as data / the file name instead of just the name of the text file itself. This is important for later. Next, we have our new verb map. With dplyr, we've been working with single data frames or combining 2 data frames. With map, we're able to apply a single call or function to a list of several data frames. In this case, our call is read.table. It's the same way we used read.table in the past to read in single files. With map, we can run read.table, but on all files in our list. This is why we have to have full.names equals true, because just as when reading in one file, we have to provide the full file name, including its location. Most of the rest of the code in this call should be familiar to you, except this NA_strings call. Basically, I'm telling R that whenever it gets a cell that is empty, it should write NA in it. This will come in handy later when we want to filter out some of our data. Finally, we're going to want to combine all these data frames together. We do this with the reduce call. Basically, we're telling R to reduce our 3 data frames down to 1 data frame. The last thing we need to do is tell R how to reduce it, which is with a row bind, or rbind. We want R to stack each data frame on top of each other in terms of rows. Pause the video now and return to the lesson. Here's the beginning of our data clean variable. Since there's a lot of code in this call, I'm just going to skip down to the new part of the code. You can assume the other code is also there, just hidden for now. First, we have a group by call, which should be familiar to you. Then, we list the variables we're going to group by. Here, series, alignment, and alien. Next, we have the verb arrange, to say that within our groups, we want to order the data a certain way. We then feed R the variable we want to order by. I chose episode, so that we take the first appearance of each alien species within our variables. Note, the default for arrange is ascending order. Next, we have our filter call. And then, how we're going to filter. Since I want the first appearance of each group, that's the same as saying I want the first row in each group. So, I use the row number call, and I say that I want row number to be equal to 1. This will drop any rows within a given group that is below row 1, giving me one data point per group, and thus only the first appearance of each alien species within my variables. And then we end with an ungroup call to remove our groupings in case we want to do more with the data later. Pause the video now and return to the lesson. Let's go over the new code for this plot. Some of the code you've seen before, so I'm not going to go over that again in detail. We start with the name of our plot, followed by our standard initial plot call. But the fill call is new. Fill tells R what variable to use to color the graph. In our case, what color to fill the bars with. It's also a way to get grouped bar plots, because first it will make bars for each of the levels within our X aesthetic, in this case series, and then within each level of our X aesthetic, it will make bars of unique fill colors for each level in our fill aesthetic, in this case alignment. This GOM bar call should also be familiar to you, but the position equals dodge call is new. This is important for our grouped bars. By setting position to dodge, we make sure the bars are side by side instead of being stacked on top of each other. With GOM hline, we can add a horizontal line somewhere on our figure. Similarly, GOM vline adds a vertical line. We use the y-intercept setting to say where we want this horizontal line drawn. In our case, we want it drawn where y equals 50 to show 50% or chance. So far, we've been using the default ggplot2 colors, but with Scale Fill Manual, we can choose the exact colors we want our bars to be. We set values equal to a vector of two colors, red and yellow. We supply two colors because we have two levels for the variable we set fill equal to, alignment. The colors will be applied in the order of the levels for alignment, so red for foe and yellow for friend. This is the end of today's video. I hope you enjoy finishing the rest of the lesson.